Okay, our next speaker is Peter Schuetz from Unilever. And again, I think Peter and I, we met about a year ago for the first time, and subsequently we had an undergraduate research student working with us over the summer of 2000.
This year.
This
summer, yes.
And I think some of that Peter will present.
Yeah.
And the title of the talk is Calculating for Pleasure. So.
Yes, so I'm a bit of the odd one out. I'm a problem owner, not a problem solver in that in the math space. I'm a material scientist, now leading a measurement team, a team of microscopists, and that's where we produce images, and that's where I will show that where the problem arises. So what I'll do the corporate bit about what is Unilever. In case you don't know, then I show you a few applied and numerical problems, just giving a flavor of it. Again, as it's not my specialty, I don't go into the depth of solving. I just give you a flavor of the very top millimeter or whatever, the top scratch of the type of problems we solve. That then you can probably imagine how they get more complex and deeper and more involved, and where actually people are where we're working on. But I just give you the very top level flavor of what type of problems we have, and then I'll show you a bit of the results of the summer student we had this summer, and where we want to extend work and work in securing contracts and things for work later next year. So yes, as you know, Unilever, you might know or you might not know, but if you don't know Unilever, you know quite a few of those brands that Unilever makes. We're a Dutch and UK company with headquarters in London, but research labs are around the UK as well. So Unilever's in foods, in personal care, in refreshment, that is tea and ice cream, and in home care, that's fabric conditioners. So yes, fairly wide range of consumer goods. All the things in supermarkets with brand labels on it, that's basically the type of things we make. But all companies now have purposes, and I think for us the purpose is a bit more, actually feeds into our research work more than with some other companies. So that's sustainable living, so all around sustainability and work. So it is help people improve their well-being and health, and that's very strong because we're the Unilever's footprint is very strong in developing markets, India, China, and in some African countries we also have a very strong basis. So there's where a strong impact can be made with soap, that's the image there, clean hands, hygiene, personal hygiene, but hygiene in an ecological and sustainable way, making the right decisions. Which, of course, over time have not always made, and there's always the balance between cost and sustainability. But now the emphasis is finding sustainable ways at the same cost. If there's two options, go for the sustainable option. And thinking of new ways of employing it. And yes, it's not a true course, but of course it's a link to it that sustainable brands grow stronger. So that's another reason that sustainability and decisions based on sustainability and marketing based on sustainability doesn't slow you down, but actually can move you on. So what do we do in R&D? In R&D in Unilever we have a number of sites. I'm in Coworth, that's, as you see there, it's quite close. It's north of Bedfordshire in the village, on a village, an old country state that was bought after the Second World War to grow peas for Captain Birdseye. The frozen peas breeding program was developed there. Now Birdseye was sold a few years back, but it's still a very nice environment. Research labs on a country home with loads of fields around that hopefully will stay fields for a few years more. And then there's other labs all over the globe. Port Sunlight, for example, that's where Unilever was founded. The Lever brothers making soap near Liverpool, and the Holland Vlaardingen, which is near to Rotterdam, where the spreads and yellow fats business came from, and now the foods research is. So I'm working in the refreshment category and more especially on ice cream. So what is ice cream? You all know ice cream comes in a nice tub and hopefully is pleasure. That's what I want for lots of people, but for us ice cream is actually far more complicated thing. Ice cream is a partially frozen foamed fat emulsion, a protein containing sugar solution, so a very multi-phase and multi-component system. So going to address this, it's quite unique because it has loads of components interacting with each other in a way that's uncommon and not easily translatable to other systems. So we normally have quite niche problems driving all things. For example, just the simple things like measurement, all has to be frozen because once you are at room temperature, it's gone. It's not like with loads of other systems that in metallurgy and other things, at room temperature nothing changes. Even if there's a hot application, you cool it down and it's still there somehow. But for us, everything has to be done in a frozen state. So it's just to iterate again, it's a four-phase system. It's partially frozen, so there's ice crystals around. It's a water in oil emulsion, so there's fat droplets around. There's a foam, there's air bubbles around, so that makes it nice and smoothie and cream, and that changes the density, for example, between a Ben & Jerry's ice cream, which has less air in it, and Carte d'Or and Cremissimo ice cream, which has about 50% face volume is air, very finely distributed, so you don't notice the big bubbles, but you distribute it in, and that's putting this in the right way. It's a very strong quality factor, how to get that, how to maintain this, how to maintain a foam over such a long time. And then you have a dispersed phase, which is a sugar solution, what we call matrix, which is sugars, proteins, and yes, sugars and proteins and biopolymers on some level even don't mix properly. So you could have another phase there, but we don't worry about that one. So that's just how you see it. There's ice, about 30% of volume, no energy contribution, it's just frozen water. Then there's air, half of the volume, and again, no energy contribution. Energy contribution here is calories if you eat it in that thing. Then you have fat, which is only 8 to 8% in some formulations. In really indulgent formulations, it can be up to 10% fat, but that just scales the energy up completely. That's a very strong contribution. That provides structure because it sits, as you see there, on the top of the air bubbles, stabilizing the air bubbles, stopping them from joining, from moving together, keeps everything in place. It boosts creaminess and drives flavors because loads of flavors are just fat-soluble flavors. And then all is embedded in the matrix phase, about 15% of volume with proteins, sugars, stabilizers. So the protein emulsifies all the fat, keeps the structure, keeps the creaminess, gives the milky flavor, gives the taste. The sugars are mainly are there once to make it sweet, but that's not the main function. Sugars are an integral part because it's small molecular weight materials that stop everything from freezing. It's like putting salt on the road in a way. The sugars are small molecules, lower the freezing point of the system. That's what keeps the matrix from not freezing. So because if you wouldn't have them there, everything would go for an ice cube. As you know, if you freeze water below zero, it's an ice cube. But as the sugar solution has a certain freezing point, it stops freezing at the given temperature, and therefore you have something unfrozen and it gets concentrated up depending on the temperature. And I'll show a bit of that later on. And stabilizers, which are gums, could be like carob gum and other plant extracts that just are hydrocolloids that get a viscosity, get a nice and creamy mouthfeel, for example. So now I'm going to show a few problems as I say, they scratch the surface, but that's problems where we put in quite a bit of effort to understand and go into more detailed modeling and theoretical, calculating the properties, doing the physics right. So this is a simple problem. So how long does the equilibration of ice content take after a temperature jump? So if we have a sample, we make the ice cream in a big freezer, cooled with liquid ammonia at the outside, coming out at -6, -5 degrees, pumped out in a big tube, going towards the handling filling stations where it's put into tubs or cut up into bits for magnums and other things. So this tube warms up from the outside, and so how long does it actually take for the ice content and all the other things to be in the equilibrium? We have pressure jumps, we have temperature jumps. How long does all this equilibration take? And the next thing, so that's where I go there with the ice curve. That's frozen solution is determined by the frozen solution. Well, the ice content is determined by composition and temperature. So if I know the composition and the temperature, I have a given amount of ice. Because if I start with a solution with the sugar molecules, and then I drop the temperature, ice starts to grow. And it starts to grow until the concentration in the liquid phase is basically at the freezing point. Because otherwise, more would freeze. Or if it's more concentrated, some would melt to just be in the equilibrium at that given temperature. So for all compositions, we know the ice content, and that can be plotted as an ice curve. That's an example. So for a more or less typical ice cream sample, we have at -5 degrees, we have about 20% ice. That's just in mass. And at -10, we have 45%, and at -20 we have 53% or something like that. So this is happening, but yes, as I said, all these temperature jumps are buffered by the massive latent heat. Ice has a big latent heat, so the sensible heat is very small compared to the latent heat to produce the ice. So you have to have a big energy flow to create ice. You know that a small ice cube can keep a glass of your long drink cold for quite a long time, because it has it's so much cold is stored in that one cube of ice. So how quick is the equilibrium on an ice crystal scale? So are there any slowdowns on the diffusion, on the ice growth, and the temperature transport? So we looked into so this model by my colleagues was parametrized, just very much simplified as a simple crystal. But of course, that's where you can imagine how things get complicated if we go for more crystals, more complex temperature behavior, and all those things, where we're actually look into modeling the whole thing. But you see the behavior, the ice grows, the concentrate, as the ice grows, the solution is concentrated up, but then has to relax back to the equilibrium state after any temperature jumps. So this is a combined heat and solute diffusion problem. So it is a type of a Stefan problem that we can solve, and we can then go into it and show that there's no problem. All those equilibration things are at given temperatures with the viscosity of the matrix and everything. We do fast enough that we don't have to worry about it in real-time applications. That if we take a sample at a given stage from our system, there's less ice than the equilibrium, or we grow ice or either distort what we see, because the ice, of course, is particulate and stops and has a very strong influence on viscosity and other things. So at least we can model the viscosities in different stages, assuming equilibrium temperature, and that we don't have to look at delays. As I say, this problem of understanding ice growth and different behavior can be driven to far more complex things, multi-crystal things, other behavior. Another problem that is somehow linked to it as you will see in the end, is frost formation in ice cream tubs. The business, that's a very applied problem that we had a few years back. The business wanted from those tubes that you might see to those tubes which are transparent there to show how nice the structure is inside there with all the flutes and tubes and sauce and sprinkles and everything distributed. And so you, the consumer, would like to buy that one on relying to see how nice it actually looks and not just relying on the picture that we print out on the top. So all this started, but on an implementation, and then the product was made, everything, all the materials were sourced, the machines were made to actually create those plastics, and then we found out that on storage, those things frosted up in that range very strongly, which of course, as you will also know as consumers, isn't a sign for quality in ice cream if it's nicely frosted up. So the question we had to address fairly quickly is, why is this happening and what can we do about this? We can get more than 4 grams of frost within a few weeks, and it can look like this, which isn't nice for ice cream. So we also quickly did the calculation that the water in the headspace at any given time is about 3 milligrams. So there's a massive flow of moisture in that system. How does it happen? And first of all, we had to look at how can we test this reproducibly. We saw this appearing in ice cream. Everyone thinks it's bad because the temperature oscillations do normal things. If you melt and refreeze the ice crystals, that's normally when ice cream goes. So we have protocols, but we use those temperature abuse protocols going from between -20, like your freezer temperature, and -5 degrees, which is perhaps what you have in your car on the way home from the supermarket. So those oscillations we did, and they actually eliminated the effect, and it wasn't as bad. So we really were stuck how to reproduce it and how to figure out what we do. So using loads of different approaches, we came up to look that here thermal oscillations tend to drive a climate system inside the tub. So we have convection flows. Where the cold ice cream that buffers the heat for longer in small oscillations just drives the warming up, and then there's convection flow, and that transports moisture up inside the tubs. And you see here that's a tub, and you see the exposed nose. That's a lab filling. So that's not. But on that nose, there's loads of frost on the top there. So we actually looked into modeling the heat flow and the weather system inside an ice cream tub while it sits in a freezer. Here we only did a 2D, another colleague of mine did a 2D model. So a warm tub placed in a cold freezer. We know that turbulence isn't properly captured, but I think because it's only 2D, it's not a 3D thing, but that's the best we could get up in the project time we had. And you see heat flow from the outside, heat flow from the inside. Everything's rising up in the middle on those mountains in the top. There's moving up. You get quite complicated turbulence around the outside for the heat flows around the tub. That's another problem, of course, where you place it, in what's your local freezer environment, what you put it next to. And we also captured moisture transport, and you might see in the top corner on the lid some green frost might appear or might not, depending which simulation I actually grabbed. Yes, now it is there. That's actually a model that captures the moisture transport and condensation and freezing at the surface again. So when we looked at that, we found a surprising solution, which wasn't very practical. Store the sample upside down, because then your thermal masses and temperature lags just change the whole behavior. And you, in the case where the frosting is the biggest problem, if you put a warm tub in a cold solution, your air layering is the right way around so you don't get convection flows, and that actually worked. The drawdown, of course, is that then all this transparent lid is not really very relevant anymore, because you don't look at these samples from the bottom in your supermarket. So the solution didn't fully satisfy all the criteria we needed. The other solution was to decrease the headspace by changing the depth of the lower part of the pack, and just increasing everything, and that decreasing headspace reduced the driving forces enough to slow down the convection flows dramatically, so this problem didn't appear anymore. And of course, the other thing, as I said there, put the bigger image on the top. Originally, it was about half open, but just a bigger sticker solved the other half of the problem. Now to the third problem. We characterize our complicated ice cream microstructures by SEM images. So that's scanning electron microscopy images on frozen samples. So we take frozen samples, we crack them at minus 80 degrees when ice cream is brittle, and then we look at the images. And we get images looking about a bit like this. And we get loads of them. We have got loads of them over the past whatever years since this technique was developed. Well before digital cameras came around. So we have some scanned-in images from actually photoplate images. So we, not SEM, of course, with photoplates, but we have some very old images, very low resolution images. So we also have information on the formulation, but we can't data mine those images, because we have the images and we can't extract features from them reliably. So all the feature extraction, if we ever need them if we want to make some tight quantitative claims for patents, we do feature extraction by getting some temporary people or students sitting there drawing images, or before putting holes in and measuring the size and stuff like that. So where am I? So as you see, again, that's a colored in picture of the microstructure. You see air cells, you see the ice crystals there, and the matrix phase. And we want to basically get ratios of all of them and sizes for all of them. So air bubble size is a very strong quality predictor. So we go through a thermal heat and cool cycle. We see, does the air bubble size change, or does it stay the same? And how does the ice crystal size change? Because if the ice crystals get too big, you get graininess in the mouth. That's bad quality. Or if the air bubbles get too big, they start linking up, and then you just have a continuous air network. And if that happens, there's a channel to the outside, and then the volume can completely collapse if everything gets warm and soft. So you get those very bad samples where you just have a bit of very dense ice cream at the bottom and nothing on the top. And those catastrophic things don't happen in good supply chains like in Europe, but if you go to some Asian countries or South America, for example, or tropical countries I don't even start with Africa, because we don't even have a ice cream business there for those regions, for those reasons, because we can't transport samples reliably between cold stores and stuff like that. So all these problems that then appear that happen on our side of the supply chain, but get even worse once people actually drive their samples home and then put them in their freezers, and there's a power cut, and what happens then? So we have to test for all of those and look for what formulation and what processing parameters make those things better. And we'd like to access all that data that we have, but for that we have to extract some more data from our existing images. As you see, I'm jumping my slides by just talking too much. you see how the structure can change between freshly made and storage. So yes, as I said this as well, we do routine image analysis, but at the moment we do qualitative things, qualitative analysis comparison, always with a control in the same set. We look at them spread out on either on screens or more often than not, if we have more than a few samples on a big table, all the printouts spread out, looking at them, looking visually. With our trained operators, our experts know what to look for, how to compare them, which one is more stable, which one is probably, they have the knowledge of what's the border of acceptability, how much change actually is acceptable and how much is not. So, but all previously tested segmentation solutions didn't meet our needs, and you can trust me, there's enough people trying to sell us segmentation solutions from the instrument manufacturers to our experts that I manage, and they tested them all, and there's unique problems in our system, as you will see. See there, there's very low contrast things. There's sometimes, that's where the arrow points, you see a bit of the matrix phase inside an ice crystal, and you want to exclude that. There is also all this lighting up, because it's a 3D structure, lighting up in the edges. We need a reproducible way to get those clusters deciding which crystals are one and which crystals are separate. At the moment, we do that by circling and rely on uniform user bias, making the same decision all the way and circling enough when circling enough crystals for it to even out, and that works well enough. But we'd like to get better, and we also have problems like this. There's, based on the mechanism of cracking the ice crystals, there's crevicing, there's a creep, there's cracking. So there's lines running across crystals. There's steps where the sample doesn't break properly, where there's cross lines, fault lines, and you see there's shallow air bubbles that are just capped below the equator, and there's those deep black holes where the bubble is just capped at the top and then extends very far below. And to get all those separate, that's our challenge to move into big data, and that's why we approached Corolla about a year ago. And we did that summer project just to see, where's Robert here as well, to look how to get from our input to the output, classifying all those blue things as air and all the yellow things as ice. And you see in the close-up, there are some hints how you get there. The ice is planar because it's cracked straight through, and then it was etched to get a contrast. It's a lower level. That's just how we actually create the contrast, by sublimating some ice away, and the pure ice crystal sublimates quicker than the matrix phase. So that's where there's ice is stepped down from the matrix on the top. So at first glance, there's three types of structures, as I said. There's the ice crystals, the flat things, then there's the deep holes, and then there's the shallow air bubbles, where they're just not as uniform. By eye, it's fairly clear to make those decisions in almost all cases. If you're trained to look at that, you might struggle, but for me it's obvious. I've looked at enough of them, even not being the trained operator using that, just being in enough meetings discussing those structures. So there's very clear differentiations. There's very few cases where we get it, where we sit there and really doubt what's actually going on, what type of structure it is. So there must be a way to differentiate it, but based on things that we see by eye. So we tried the convex relaxation with the two-means clustering. So based on texture in the way of local texture, and you see this worked fairly well. By hand, the clustering is just a bit larger, but but we get the main features out. We also, or not we, but Rob and Christiane tried machine learning classification. So tried on based on neighboring pixels, can it be trained? And you see there for quite a large number in a very short time, it with very limited data, it seemed to work fairly well. So that gave us confidence to move on and try to do a more in-depth work next year. Yes, so the conclusion is very good progress in the initial things. A number of approaches looks like they might work and we might get somewhere, so we'd like to continue with that. Thank you.
Thank you, Peter. Questions?
So in the segmentation problem that you were describing,
Yeah.
Are there errors that you care about more than other kinds of errors? And is there a sense for like what kinds of mistakes are most costly?
I don't know that much about all those things yet. I know that with the classification, we don't have to be 100% accurate, but we'd like to be able, as a first step, if we'd like to be able to classify a non-classifiable structure rather than a false positive or a false negative. So we should be able to throw out those. If we could just throw out all the ones with lines running across it reliably and just not address them, that, for example, would be a step on our problem. We know if there's a problem, but again, we'll have to see how we approach it. It is new to me because at the moment we're doing it by hand, and those problems are always there but never obvious. They're never really talked about. You come up with a solution and someone makes the decision. So I think we have to address quite a few of those things once we actually go into more automated solutions.
So you also mentioned limited data. Is that because you have to have this human annotation of the images?
Yes, there's number of limitations. First of all, this was a very short summer project that went amazingly well and quickly. The other thing is we have sets of images, but we have only limited sets that are hand classified as training data. So yes, as I say, we normally just do that for some few patent applications where it's very critical to separate out numbers and where we patent based on size criteria that can only come from one process or one formulation and stuff like that. So if something like this is even considered, people run from the project because they don't want to sit there days and days doing the circling. So yes, it is limited for that reason.
But if you didn't have the restriction of having label data,
yeah,
would you be able to generate a lot more unlabeled data?
Unlabeled data, yes, we have hard drives full. That's just the decision. The question. Yes, at the moment it is accessible, but there's the additional limitations from us being industry. I have to go through a kind of a process to look what's actually suitable and to be released from our numbers of web pages, even as unlabeled data. But that's an internal, completely separate issue. But we have enough data, and once we have that, we can create a lot more. For example, just having imaging a whole area. We normally take samples and we image subsets, because what do we do with all the data? But if that's needed, the operator just doesn't change the sample after 10 images, but records the other 50 that he could record, but doesn't care at the moment. And then we have far more data.
The number of these kind of trees here, is it tens, hundreds, thousands? What sort of ballpark?
Sorry? Number?
Your training data.
At the moment we have those.
I think, Rob, you can maybe answer what has been used
currently
here.
2 images.
Yes, but of those resolutions, if our instruments work, we create about, 4 days of operation, 4 samples, 10 images per sample, so about 200 images of those we do during a week. Of course, not all of them, and about probably half of them are just standard things, and the dynamics might change once we can do more things with them and use them to generate big data as well. We might capture more images of more samples. At the moment, it's with a qualitative analysis, we go for. It's only worth if we expect some big changes, and not all samples can actually go in. But that, depending on what we can actually do with the data, that will again shift and change.
Lunch? Okay.
Yeah.
Let's thank Peter again. Thank you very much.